Welcome all. Today we will see a new topic, direct and indirect semiconductor. Otherwise precisely telling it is direct band gap and indirect band gap semiconductor. So we have seen the electron is having both particle and wave nature. So the particle wave nature of electron, the likelihood of finding an electron in a particular location is described by a wave equation. And the wave equation for an electron assumed to move in x direction is given by psi k of x is equal to u kx comma x into e raised to j kx x. Okay, where psi k of x is the wave function that is given by a u function into e raised to j kx x, where kx is the wave factor or propagation constant, and u kx x modulates wave function according to the periodicity of lattice. That means an electron will travel within a lattice structure periodically, or the movement will be periodic. So modulates the wave function according to periodicity of lattice. The propagation constant k is also known as wave vector, and it is of a sinusoidal electromagnetic wave is a measure of change undergone by the amplitude and phase of the wave as it propagates in a given direction. Okay, so propagation constant k is nothing but it is a measure of change undergone by amplitude and phase of the wave as it propagates in a given direction, say x direction. Okay, so the wave vector k of a plane wave is a vector which points in the direction in which the wave propagates. So in which direction the electron moves, that is pointed by this wave vector k. The magnitude, its magnitude is the wave number as defined by the wave number k is equal to 2 pi by lambda, where lambda is the wavelength in the medium. The value of allowed energy can be plotted as energy, the value of allowed energy can be plotted versus k. That means we can plot this particular momentum of electron can be plotted by having a x-axis the momentum factor k and y-axis the energy. So energy versus k, or ek diagram. Energy stands for E and k stands for the momentum. Okay, the periodicity of the lattice structure is different in various directions, so the actual plot of EK is a three-dimensional one. Here we are giving just an introduction about the wave nature of electron. That electron got a momentum, and that momentum can be represented by a propagation constant k, and the the nature of the electron movement is given by this equation. Psi k of x is equal to u kx of x into e raised to j kx of x. That is, the u function modulates, it's a modulating function, wave function, according to the periodicity of lattice. So this is just an introduction type. Now we will move on to what is actually the direct and indirect semiconductor. So in semiconductor physics, the band gap of a semiconductor is of two types. They are a direct band gap and an indirect band gap. So we know the solid have two band formation, or else an isolated atom have different energy states, like innermost orbit having certain discrete energy, then the second orbit having certain, outer orbit having different energy states. But when these isolated atoms bonded together to form a solid, then there is no concept of discrete energy level. The energy level is converted into band of energies that we have seen in the last class. So band of energies, we have three types of bands. They are valence band, conduction band, and forbidden energy band. So valence band, conduction band, and forbidden energy band, EG. So we know this, right? So here, what is direct band gap and what is indirect band gap? Okay, so you can see here the band gap is called direct if the crystal momentum of electrons and hole is same in both the conduction band and valence band. So we have seen the conduction band got the minimum value as conduction band minimum, and the valence band maximum is notated by valence band maximum energy EV. So what is direct band gap? That is the electrons and holes present in the conduction band. The momentum of electrons and holes present in the conduction band and the valence band, if it is same. Okay, that is the band gap is direct if the crystal momentum of electrons and holes is same in both the conduction band and valence band, or the conduction band minimum and valence band maximum is if it is having same momentum for the electron, then it is direct band gap semiconductor. And then what is indirect band gap semiconductor? The momentum of electrons present in the minimum of conduction band and maximum of valence band have different momentum. If the momentum of electrons in the conduction band and valence band are different, then it is indirect semiconductor. Okay, so hence an electron can emit a photon. So what they are telling is, this is the conduction band and this is the valence band. So this can be explained by plotting a EK diagram. EK diagram means K is the momentum and E is the energy. EK diagram, EK plot. Okay, so if the minimum of the conduction band and maximum of the valence band are at same K, that is K is equal to 0 here. At same K, K is the momentum or propagation constant K. As at the same momentum, then it is direct band gap semiconductor. So during optical excitation or thermal excitation, the completely filled valence band have many electrons, right? They will get excited and they will reach to the empty conduction band. For current conduction, electrons will get excited from the valence band to the conduction band. Okay, so as Pauli's exclusion principle says, the electrons are not at all stable at a higher states. At higher states, the electrons are not at all stable. So they have to come back to the lower state. So the electrons present in the conduction band has to come back to the lower valence band. So the energy acquired by the electron in the conduction band has to be released. That will be released in the form of light or photons. The electron can directly emit a photon. So if the momentum of the electrons or holes present in the conduction band and valence band are same, then when the electron are coming back to the lower state or recombination happens, right? So the electrons in the conduction band coming back to the valence band, the extra energy will be lost in the form of photons or as light energy. So the example for direct band gap semiconductors are compound semiconductors, say gallium arsenide, indium arsenide, then we have gallium nitrate, GaSb, indium phosphide, etc. So they are examples of direct semiconductors. So you can see the EK plot here, EK plot of direct semiconductor. So you can see this is the conduction band and this is the valence band. So electrons present in the conduction band will be coming to the lower energy state by releasing photons, so h nu. So we know the difference between the conduction band energy and valence band energy is nothing but the forbidden energy gap Eg, or else I can write EC minus EV is equal to Eg. That difference in energy will be given as light energy or emission of photons is happening. So now you can understand this is the working principle of LED, light emitting diode, and other lasers, semiconductor light emitters and lasers. This is the working principle. For making an LED we should use semiconductors which have direct band gap. Now coming back to indirect semiconductor or indirect band gap semiconductor. In indirect band gap, the momentum of electrons in the conduction band and valence band are not same. They are not at the same momentum. Okay. So when an electron in the conduction band has to recombine with the empty state in the valence band, what have to be done? There should be a change in momentum. There should be a change in momentum because both the states are at different momentum, right? So there should be a change in momentum. So the electrons in the conduction band will go to a defect state ET, then from there it will come back to the valence band. So in indirect band gap semiconductor, a photon cannot be a photon sorry In indirect band gap semiconductor, a photon cannot be emitted because the electron must pass through an intermediate state ET and transfer momentum to the crystal lattice. So if I am drawing the figure, this is the conduction band and this is the valence band. These both are not at the same K. The K value are not same. So we will draw it like this. This is the energy state, this is the conduction band, and this is the valence band. So the conduction band minimum and valence band maximum is not at the same K value. So what has to be done? An electron in the valence band has to reach the electron in the conduction band has to reach the valence band. So it has to move to an intermediate state ET, and from there it has to go to the valence band. So the momentum of the electron in the conduction band has to be changed and it should reach to a intermediate state, and from there it has to come to the valence band. So the energy difference here, it is not emitted as photons, just heating up of the lattice will be happening. The solid lattice will get heated up. There will be a thermal energy generation will be there. There won't be any light emission. So the example for indirect band gap semiconductors are elemental semiconductors like silicon, germanium, and some compound semiconductors also are there like silicon carbide, silicon, germanium, and silicon carbide. So here the figure, both figure are drawn together here. So the first one is the direct band gap semiconductor EK diagram, and the second one is the indirect band gap semiconductor EK diagram. So you can see in the first one, this is the conduction band, this is the valence band, K in the x-axis and E in the y-axis. Both the states, that is a minimum of the conduction band and maximum of the valence band, are at the same K value, that is K is equal to 0. So when an electron in the conduction band coming back to its original stable state, the extra energy Eg is released in the form of light h nu, that is equal to Eg. Whereas in the indirect band gap semiconductor, the minimum of the conduction band and the maximum of the valence band are at different momentum. You can see the K value is different. So the electron will first come to a defective state ET, then it will come back to the valence band. Okay, so here there is no light emission. The extra energy will be emitted as temperature or thermal energy. Heating up of the solid happens. So altogether I'll read it once. The direct band gap semiconductor, the minima of the conduction band and maxima of the valence band occurs at the same value of K. So an electron making the smallest energy transition from the conduction band to the valence band can do so without a change in momentum. In indirect band gap semiconductor, the minima of conduction band and maxima of valence band occurs for different values of K. Thus, the smallest energy transition for an electron requires a change in momentum. Electron falling from conduction band to an empty state in the valence band is known as recombination. The recombination probability for direct band gap semiconductor is much higher than that of indirect band gap semiconductor. The direct band gap semiconductors give up the energy released during this transition, that is Eg, Ec minus Ev, in the form of light. And this property is used for optoelectronic devices like LED and lasers. The recombination in indirect band gap semiconductors occurs through some defect states within the band gap, and the energy is released in the form of heat given to the lattice. So this much about direct and indirect band gap semiconductor.